One of the most important areas of electricity and magnetism involves capacitance. Capacitors are used in many applications. Here's showing you pictures of some capacitors. These are small, these are medium, and these are large. Large capacitors, for example, are used in power supplies where you're converting AC voltages to direct current voltages. And these are used basically to smooth out waveforms so that you get close to a DC output. Well, one of the most common capacitors are parallel plate capacitors, and we'll consider parallel plate capacitors that are equivalent to having infinite plates. The dimensions of the plates are infinite. The reason for doing that is because then we can ignore the fringing fields at the edges of the plates. Fringing fields occur for any finite plate size. So what we're talking about then is that this area, so the length of these sides that create this area A, are much, much larger than the separation D. Then we have a good approximation to this case of finite and infinite plate size. So calling the top plate the conductor 2 and the bottom plate conductor 1, if we look at the side view here, here's the top plate and the bottom plate. We'll call k hat the unit vector that goes in the direction between the bottom to the top, and it's in the direction of increasing z. And if we take this position as 0 and this position d, we'll get, of course, the separation d. Well, these have potentials applied to them. We're going to take this one to be 0, so that's equivalent to having it at ground potential, like that. So then if we apply the top plate, if we apply a voltage V12, then the difference of potential, delta V, is just equal to V12. Well, we can determine the potential as a function of Z by using Laplace's equation. And so if you remember, Laplace's equation in Cartesian coordinates look like this. We have the second derivatives or second partial derivatives as a function of x, y, and z. And so if we write that then in terms of the Laplace's equation, it says that del squared v is equal to 0. But because this is only a function of z, these two terms give you 0, and so you're left with Laplace's equation looking like this. And so we have the second derivative with respect to z operating on v of z, and that's equal to 0. Well, then we look at the boundary conditions, and we've already stated what those are, namely that the voltage applied to the bottom plate is 0, and the voltage applied to the top plate is V12, z equals 0, z equals d. So doing that, we first solve the general case. So we take this equation here, integrate twice, and we end up with a simple function like this, the linear function with arbitrary constants c1 and c2. So the linear equation here, and now we apply our boundary conditions. So here's our first one. So if we look at that, setting z equals 0, this cancels this term here, that's 0. So we're left with c2, and that's equal to 0. If we go to z equals d, we have that equal to v12, and so that means that putting in z equal d, we'll have c1d here, and that's what we show here. And that means then if we solve for c1, it'll be the voltage v12 divided by d. So putting that into the final result, this is the potential as a function of z between the plates, and it's the magnitude of delta v, or v12, divided by d times z. Well, given that equation for v, we can find e by just taking the gradient and putting a minus sign in front of it. The gradient operator in x, y, z looks like this, and this should be an x right here, but we're going to throw it away because v only depends on z, and so this term and this term disappear, and we then have that the E field will be equal to this derivative times the unit vector k. So taking our potential equaling v12 over d times z, taking that derivative, we're left with the E field being minus V12 over d k hat. So again, our picture of the capacitance, and we have the E field defined in this region right here. And if you look at that, then here's the result that we got. The E field is in the opposite direction, so it's in the direction of the normal to surface 2, or minus k hat. So minus k hat times V12 over d, which is the magnitude of E. So the E field inside the parallel plate capacitor, as you probably know, is uniform and goes from the plate that is positive, assuming V12 is positive, to the negative plate, which is at V equals 0. And remember that if you have positive charge here, and this is a conductor, it would induce negative charge on the inside surface of this plate. So this is plus here, and this is minus here. And I draw the little pluses here to indicate that the surface charge is on this inner surface here. Well, we can find the surface charge density using the field that we've just derived and applying Gauss's law. So here's the same problem drawn a little differently. We've got our k vector in the direction of increasing z. This is the minus plate, this will be the plus plate. And what we do is we draw a Gaussian surface here, and if you wanted to, you could say that it looks like this. So it would look like that, where this is A and this is A back here. The sides are parallel to the field outside. The E field is in the direction from plus to minus. The normal vector to this surface is in the minus k direction. And inside the conductor we have E equals 0. So what that means then is that if we do the Gauss's law result, remember that says that the integral over the surface of the pillbox of the E field dotted into the area element ds is equal to the q inside the pillbox divided by epsilon 0. So for our simple geometry, if E is parallel to the z-axis and this surface is parallel to the z-axis, then there's no E dot ds along the sides of the pillbox. Remember, E is 0 here, so the only surface that we have to look at is this one out here. So given that, we have E times A as the integral of E dot ds, because the field is uniform over that surface. So it just becomes E times A. Q inside over pillbox of the pillbox over epsilon 0 is the surface charge contained inside, so that would be this surface charge here divided by epsilon 0. So if we divide by A, then we'll have Q surface divided by A. That's the charge density on this surface here, and we've rearranged by multiplying by epsilon 0 both sides, and so we have the surface charge on 2 is equal to epsilon 0 times E. Putting in our equation for E, V12 over d, then this is the surface charge density on the plate. The surface charge density on the opposite plate could be also calculated, and that will end up being just minus this quantity here. So if we evaluate the total charge on the conductor 2, here's the surface charge density that we derived, then it'll just be the area times this surface charge density. We'll call that capital Q, and so this will be epsilon 0 V12A divided by d. So we want to evaluate the capacitance, and so we have to ask, what is the capacitance? Well, the capacitance in words of a two-conductor system is the ratio of the total charge on one of the conductors to the potential difference between the conductor and the other conductor. So in other words, if you have these two conductors here, just labeled V2 and V1 as their potentials, those potentials determined in terms of the relative values by thinking of a battery connected between these two conductors. And so the way I have it here, this would be plus and this would be minus. Applying this potential would put positive charge on this conductor and minus charge here, because if we put positive charge here, it will induce negative charge over here and vice versa. So this is delta V that we've applied between the two conductors, and there will be a V12 like we had before, which will be equal to delta V, V2 minus V1. So the capacitance then will be the Q that's induced on either of these conductors because they were equal. The Q is positive for calculating the capacitance if V12 is positive. This is a positive quantity, so if you get the wrong sign, you just throw it away. So that'll be Q over delta V. That's the definition of capacitance for a two-conductor system. So repeating then, this is a positive quantity. The units of capacitance are farads, which is a huge number, by the way. Capacitance is a measure of the ability of a conducting configuration to store charge. If Q is the charge on one of the conductors and V is the potential difference between the two conductors, then C is Q over V or Q over delta V. So let's evaluate the capacitance for a parallel plate capacitor. So recalling that the total charge on plate 2 is equal to the surface charge density times the area of those plates. And so putting in our sigma, which is given by epsilon 0 V12 over D, times the area, A, this gives us the Q, total Q, on one of the plates. So then C is Q over V12, and so we simply take this, and you'll notice that you're canceling this V12 with this V12. And so you're left with the equation for the capacitance epsilon 0 times A divided by D. Well, let's consider the capacitance of an isolated conductor, single conductor. And what is that? It's the capacitance that can be considered to be equal to the capacitance of a two-conductor system where the second conductor is at an infinite distance away from the first and at ground potential. So what we're looking at then is a conductor that has a charge Q located on the conductor, which would of course be on the surface, and the potential at which this conductor exists. So the other electrode is the really big grounded conductor in the sky. So this would be at infinity. So we've got a capacitor then between this conductor that has charge Q and the really big conductor over here. This is at V at infinity we set equal to 0. And you could think of it this way, that if this is a small conductor and this is really big, then the induced charge density on this really big conductor would be very, very small. And associated with that would be a potential, which would be very small, and we'll take it as 0. So if Q is the charge on the single conductor, and V is the potential of that conductor relative to V equals 0 at infinity, then the capacitance is just the Q divided by the V. Q is the charge on the conductor, V is the potential on the conductor. Well, let's take a case where we have an isolated sphere of radius r. Here's the radius r conductor. We put a charge Q on the sphere, and we know the potential of the sphere relative to grounded infinity, and what that is the charge on the conductor divided by its radius times k, 1 over 4 pi epsilon naught. This came when we derived the potential due to a charged sphere. So taking C as Q over V, we have Q here, we have V right here. So then we simplify by just canceling Q and bringing K, 1 over 4 pi epsilon naught to the top, and so we have 4 pi epsilon naught R. So the capacitance doesn't have any Q's in it, it doesn't have any V's in it, it's a constant. It only depends on the radius of the sphere. So we have a constant times a constant, so we get a constant value, which is the capacitance. So, as I said, a larger sphere, larger r, has a higher capacitance. Here are a few URLs where you can find PDF files which go over the same material in different ways, and so you might want to try looking at one or two of these. So some related topics that we're going to be covering are dipoles in a little bit of detail, the nature of dielectrics, because dielectrics will influence capacitance, the concept of polarization in dielectrics, and how that actually affects the capacitance when we insert dielectrics.